So in this video we're going to talk about the most important factor that sculpts landscapes, and that's running water. So this is the basic hydrologic cycle, which you're probably familiar with. So water can be stored in the atmosphere as water vapor, and it comes down as precipitation, it goes up as evaporation. It can be stored in the oceans, and a lot of that gets evaporated to the atmosphere, precipitation falls in the oceans. There's groundwater, so some of that water infiltrates into soil and into porous rock. But then there's surface runoff, right? So when precipitation runs in streams and lakes down to the ocean, and that's the thing that does a lot of sculpting of the surface of the earth. So let's think of a stream, or any river or stream, as a system, right? So in any stream network or watershed, we've got three zones. So upstream we have a zone of sediment production, right? So this is where we've got the headwaters, so these little tributary streams that all sort of feed into each other and join the main stream. And in this part, the stream has a steep slope or a steep gradient, and so the water is moving very fast. It has a lot of energy to erode, so it can cut down in the channels, so it's cutting these channels deeper, and it also erodes headward, so the channels get longer. They cut upstream as well. If we go down to the second zone, we have a zone of transportation. So here we're not generating a lot of new sediment, and we're not depositing sediment, we're just sort of moving it along. Sediment gets deposited in some places and eroded in others, but there's no net gain or loss of sediment. And this is where we have usually a meandering stream. We see these winding meanders in the stream. And this is where we have a well-developed floodplain. It's still got a gradient, it's still got a slope. It's not as steep as the slope in the headwaters, but it's got a lot more water in the channel, and it's got a less steep gradient. Then at the bottom of any stream network, we've got the zone of deposition. So this is where the stream meets the ocean or whatever local base level is. And this is where the gradient gets very shallow or zero, and the water level slows, or the water velocity slows down, and the sediment drops out. And then when we think about stream networks, we talked about this in the first video, but we've got this idea of drainage basins or watersheds. And so this is a divide, right? This is a high ridge running along the top of this ridge. And basically everything on this side of the ridge flows down into this stream. So this is stream A, and everything on the other side of the ridge flows down into stream B. So the divide is the high point of land between drainage basins. And we've talked about this in Colorado. So here I can draw two of the rivers on the east slope of Colorado. So here's the Platte River going this way up into Nebraska, and here's the Arkansas River going this way into Kansas. And we can see the high point between them. If you look at these elevations in yellow, this is what's called the Palmer Divide. This is an area of higher elevations. If you drive south from Denver to Colorado Springs on I-25, you'll go over this. And it's a high region that separates these two watersheds. So all the tributary streams in the south flow into the Arkansas River. All the tributary streams in the north flow into the Platte River. So there's just an example of a divide. And the concept of drainage basins is really scale dependent, right? So for instance, in the bottom here we have the Yellowstone River drainage basin. So anything that falls in this area of land is going to flow, any precipitation is going to flow into the Yellowstone River, into one of its tributaries, and then eventually into that. But the Yellowstone River is part of the Missouri River basin, and the Missouri River flows into the Mississippi, which drains 2/3 of the United States, right? So these drainage basins scale up. So streams transport a lot of sediment, and so the sediment in a stream is called the load. And the load has different components. So first there's the dissolved load, and so the dissolved load is salts and soluble minerals that are soluble in water and are just moved along. So things like calcite, the main mineral in limestone, gets dissolved in water and is carried in the dissolved load. We also have the suspended load. The suspended load are small particles that are moving in the water column and are transported by the water, right? So as long as the water is moving, there's probably going to be some suspended load. The smallest particles will be suspended. As the water, faster water, higher velocity water is going to transport more sediment in the suspended load, and slower moving water is only going to have some really fine stuff. And then finally, our largest particles are in the bed load. So the bed load is our large particles, and they either skip or bounce, we call that saltation, or they slide or roll along the bottom. And again, we can move larger particles with higher velocity water along the bottom of the stream. So here's an example of a stream near the headwaters. This is the Yellowstone River close to its headwaters in the northern Rockies, and what we see is a steep V-shaped channel, right? This is upstream in the zone of sediment erosion, sediment production, where that stream is cutting down in its channel and eroding headward. And further down, when we're in the zone of sediment transportation, we get we have a meandering stream, and that carves a floodplain. So this sort of flat, broad valley is called a floodplain. And the way that a floodplain works, the way that we develop it, is look at this cross-section of a stream channel up here, right? So here we have the cross-section, and the area where the water is moving fastest is always at the top of the channel in the middle, so indicated by the dark blue here. And the reason that we have the maximum velocity there is because that's the point that's farthest away from the stream channel, right? So the stream channel, the bed, produces friction on the water as the water moves, and so it slows it down. So the farther away you get from the stream bed, the higher velocity of the water. Now, as the stream moves, right, so as it curves through these meanders, that zone of high velocity water is going to scrape up against the side of the floodplain, right? So here we can see the maximum velocity here at this point is carving away at the side, and that's what widens that floodplain. That's what makes this nice, broad, smooth valley, is as we go into a meander, that high velocity water on the outside of the curve will carve away. And that's a formation, that's called a cut bank, right, where the high velocity water is carving away at the edge of the floodplain. The edge of a floodplain is called the bluffs, and so we usually get cliffs or something like that. Now, because the highest velocity of the water goes to the outside of the curve, the slowest velocity water is at the inside of every curve. And so, as the water slows down, sediment gets deposited. Sediment drops out of the suspended load. And so that little, that point of deposited sediment, that's called a point bar. So in every meander, we have a point bar and a cut bank. And these things are dynamic, right? So meanders, they meander, they move around. They become curvier and straighter over time. So you can see through this sequence of diagrams here that as the meanders get steeper, we're going to get, or as they, over time, we're going to get more sediment built up, and we're going to carve away more of that cut bank. So over time, the meanders get more sinuous. They get curvier. And eventually what happens is, if you can imagine this cut bank wearing away here and this cut bank wearing away here, eventually the neck of this meander gets so narrow that the stream can just cut through and take the shortest path. And so then we get an abandoned meander, and we call that an oxbow lake, and eventually those dry up. So floodplains are very dynamic over time. So we can see here the evolution of a floodplain. So here we have a fairly narrow floodplain that's been carved by the migration of those meanders, carving away at the bluffs and depositing sediment in between. And here's a well-developed floodplain. So over longer periods of time, the channel has meandered farther and farther across and widened the floodplain. We can see traces of old oxbow lakes on here as the stream has changed path. Now, the other thing that happens on floodplains is, well, we have floods. So at times of high water, when we have maybe a lot of snow melt or a lot of seasonal rains or something like that, or just an unusual amount of rain, the water comes out of the channel and fills up that floodplain, right? So you can imagine we have a lot of water, a lot of precipitation or something, so that water is rushing down the channel, and we get more and more and more water in the channel. Eventually, the water goes over the sides of the channel, and so that flood debris comes out. The water slows down very rapidly once it's out of the channel, and so the water velocity decreases and all that sediment comes out. And so we can see in this diagram all of these floodplain sediments. Those are called alluvial sediments, stuff that's carried by a stream. And so floodplains are carved by the meanders, and they're also filled with flood sediments. Now, any stream or river is an equilibrium system, right? It always wants to come back to an equilibrium. So we want, what the stream wants to have by its nature is a nice even gradient from headwaters to base level, right? So base level, ultimate base level is always the ocean. So if we have a situation where we've got a nice even gradient or slope, we call that a graded stream, right? So it's got a nice equilibrium situation. We have a zone of sediment production in the headwaters, a zone of sediment transport, and then a zone of deposition at base level. But if something happens to change that, the stream is going to work to get back to equilibrium. So let's say we have a fault right here, and what that fault results in some uplift of the land upstream towards the headwaters. So now we have this nick point, right? We have an area where the stream has new energy, the gradient has now become steeper in through here. So the stream has higher velocity, new energy to erode. So it's going to erode away at that nick point, and we might have waterfalls. Over time we might have rapids, but the stream has that new velocity to erode down. And given enough time, it will come back to a graded condition. It'll wear away that uplifted area. So we can get really interesting landforms when we have this. So imagine here in this panel we can see we have a floodplain. We have a well-developed floodplain with meanders and cutbanks and point bars. But then we have some uplift, right? So this is in Utah, in southern Utah, near Canyonlands National Park, we had this situation. We had a graded stream with floodplains, and then we had uplift. So the land gets uplifted, and now the gradient is steeper, so the stream has more velocity and more energy to cut down, to erode down in its channel, and so we get something like in this photo A, where we have what's called incised meanders. So we have these meanders running in a steep, deep canyon. So uplift of the headwaters of a stream effectively lowers base level, right? It makes a bigger difference between the elevation of the headwaters and sea level, and so that causes the stream to cut down. Now we can do the opposite. We can basically raise base level. And so if we look at this, here we have in the top panel, we have a graded stream, right? We've got equilibrium with a nice adjusted slope. But let's say we build a dam on that river. So in the lower panel we've got a dam, and what we've effectively done is raise base level, because now the new base level, instead of being the ocean upstream, the new base level is the reservoir behind the dam. So what happens here, again, the stream has to come back to equilibrium. So if we have a new higher base level, this is the area where the water is going to slow down, because it's going to hit the reservoir, and it's going to that's going to slow down the velocity of the water. And so with the slower velocity of the water is going to drop its sediment load, so it's going to deposit. And so now we see the stream is building up. It's building up basically a delta into that reservoir, because we need a gradient, because the stream has to flow downhill. So it's going to build up that, the sediment's going to drop out, it's going to build that out. So now we have a new base level, and we're going to deposit a bunch of sediment. Eventually the reservoir will kind of fill up with sediment, because we've got all this sediment now being deposited at the new base level. Now what happens downstream is also really interesting. So we let the water out of the dam down here, and so that water that comes out is clean, right? All the sediment, it doesn't have sediment in it. All the sediment dropped out in the reservoir. So what happens downstream of the reservoir, now we have this clean water coming out, and clean water has more ability to erode, because it's not carrying any sediment, so it can pick up more sediment. It has more capacity. So downstream, with this clean water released, what's going to happen to this channel is it's going to be scoured out. It's going to be any gravel bars and sand bars and things like that are going to be washed away and then deposited down here at ultimate base level. This makes a big difference if you're an invertebrate living in that stream that relies on stream channels and gravel bars. It also makes a big difference if you're a salmon and you need to spawn near a gravel bar or something like that. This is a big issue in a lot of the West where we have a lot of dams. and it actually really kind of messes up the ecosystem of a stream, because we no longer have periodic floods that move around these chunks of sediment, and the sediment gets washed away. So building a dam on a stream has big consequences both upstream and downstream.